Hi, good morning, good evening.
Good evening, sir.
We start in 5 minutes or 3 minutes?
Yes, sir. We will start now, sir.
Okay, thank you.
Thank you, sir. Good day, everyone. Now the technical session 3B on application of technologies in meteorology will start. Chair of this session is Dr. G. Srinivasan, Chief Scientist for Climate Applications, RIMES, Thailand. Co-chair of the session is Professor Dr. Mohammad Jillur Rahman, Department of Disaster Science and Management, University of Dhaka, Bangladesh. I'd like to request session chair and co-chair to start and conduct the session. Before starting the session, I'd like to request chair and co-chair to evaluate all presenters according to the prescribed format and send us as soon as possible. Thank you all.
Thank you. Thank you very much. And thanks to the organizers for giving me this opportunity. And on behalf of the co-chair, Mr. Professor Rahman, I welcome you all to this very interesting technical session 3B on applications of technology in meteorology. So we have 5 presentations to go. So there is, I think the organizers have allotted 15 minutes for each presentation. And then I kindly request all presenters to keep to time so that we can have some questions and discussion. And it's a pleasure to be with all of you, and thank you very much. I now without, if my co-chair wants to say anything, Professor Rahman. Okay, so I think we can straight away go to the presentations. So we have our first presenter. The presentation is on monthly and diurnal trends in lightning over the Indian subcontinent, a thunder hour analysis. So I request Elizabeth D. Gangi from the Earth Networks to make the presentation. Thank you. Over to you, Elizabeth.
Thank you. Good morning from the United States. I'm happy to be here. I will share my screen now. So today I'll be talking to you about, as the chair said, monthly and diurnal trends in lightning over the Indian subcontinent using an old analysis method repurposed called the thunder hour. Some background on this subject. Lightning data is increasingly of interest to those studying climate science. It has even been called an essential climate variable. This is because changes in lightning over time reflect changes in convection. And lightning can also impact the chemical composition of the atmosphere. The longest published lightning climatologies are analyses of thunder days, which are days during which thunder can be heard from a given location. Most thunder day observational studies predate large-scale total lightning detection networks because people have been recording observations of thunder for many decades. In this study, however, we're using thunder hours, which are defined as hours of the day during which thunder can be heard. Why choose this variant on thunder observations, you might ask? Well, satellite-based lightning observations, which are those that have been used to make most of the recent lightning climatology studies, require sweeping assumptions about the quantity of lightning signatures in both time and space. And part of this is that, for example, you need very long integration periods to smooth out biases from infrequent strong storms in flash density climatologies. This is not necessary when using thunder observations. Thunder hours allow a study of diurnal trends in thunderstorm activity as well as seasonal trends. It represents a sort of optimal middle ground between flash density and thunder day observations for lightning climatology. Your average thunderstorm around the world lasts for about 1 hour, so thunder hours are also an intuitive measure of thunderstorm frequency. And because we only count 1 flash per hour as an observation, the trends that you see in lightning behavior give the same weight to both weak and strong storms. Most importantly, however, using thunder observations that have been converted from lightning observations allows you to ignore variations in lightning location system detection efficiency. So the goal here is to present a preliminary but broad analysis of the Earth Network's Global Lightning Network thunder hours climatology, specifically in this case for the Indian subcontinent. To sort of show you how we calculated these parameters, we converted 5 years from January 2015 through December 2019 of Earth Network's global lightning data to thunder hours by modifying the typical thunder hours criteria. Normally, a thunder hour would be an hour during which a person heard thunder at a given location and recorded that observation. However, since we're using global lightning detection, we instead modified it to be a UTC hour during which lightning was located within 15 kilometers of a given grid cell in our analysis grid. This calculation was made using a 0.05 degree grid for the entire globe. If lightning was located at a specific latitude and longitude, we searched out all of the grid cells on this 0.05 degree grid, which were within a 15-kilometer radius of that lightning stroke. If that was the case, then that grid cell was marked as true, or a numerical, just a pure 1 value. Otherwise, that grid value was false. So in this diagram here, the blue-filled cells all were considered to be within 15-kilometer radius of this example lightning stroke. And so these grid cells would have all been marked with a 1. And then the white cells that are left blank, since they're outside the radius, would be left 0. That's for a given hour of the day on a given day of the 5-year climatology. We then calculated the probability of thunder as the number of true thunder observations from this data set for each grid cell divided by the total number of observations counted for that grid cell, which gives us a probability of thunder for each UTC hour, and we averaged them over each month of the year using these 5 years of data. What this basically tells us is, based on a 5-year climatology of lightning data, what is the probability that a given location will experience a thunderstorm at that hour of the day during that month of the year? Now, this is a view of the global thunder hours lightning climatology that we put together. It is an animation that goes through each hour of the day and each month, and we have colored it to represent the percentage chance of thunder heard at a location. The shades of yellow are where we have local daytime, and shades of blue are where we have local nighttime. It's a pretty mesmerizing animation. I've stared at it for many hours at this point. There's a lot of value you can already see when observing this cycle. There's large scale features in convection that we've documented previously in lightning climatology show up. Different monsoons, the location and migration of the ITCZ, orographically enhanced convection, sea breeze convection, all of these things show up in this climatology. And also areas that experience frequent synoptic scale meteorological phenomenon. As such, we've decided to, in this larger study that I've been working on, I've been delving into different regions of the world to look at some of the local details that we can pick out in this climatology. And so for here, I will now move on to showing you just a zoom of the Indian subcontinent. So some of the patterns that I've been able to pick out with my relatively limited expertise on the area is that during the pre-monsoon months or boreal spring, there appears to be a pretty strong diurnal signal, especially along the coasts, where we see higher probabilities of thunder at the coastline, likely the result of some sea breeze convection. There's also a strong nocturnal signal in over eastern India and Bangladesh and over the Bay of Bengal, which is likely due to the typical nocturnal mesoscale convective systems that you see in that region. We also see during the daytime deep convection along the Himalayas and Nepalese highlands, which has been documented in past studies as well. And this shows up, as I see the animation is cycled here, as a strong daytime maximum over that region. During the monsoon months in boreal summer, we see, as we would expect of the monsoon, a widespread daytime convection across the region. That deep convection signal along the Himalayas is also still there. And then there's also a nocturnal signal in that region, which is, we've looked into some of the explanations for that as well, but that is also a subject that's been covered by many past studies. And then in the post-monsoon, in autumn, there's a much lower probability of thunder across the entire region, with the greatest chances of hearing thunder concentrated along the coasts again during October. And as an example for how we can look at the diurnal seasonal trends in this analysis, for this entire region, we looked at the mean probability of thunder for each season of the year at each hour of the day. And I've started this at 18 UTC to try and capture the local daytime into nighttime shift. So the summer monsoon months, June, July, August, have the greatest probability of thunder at all hours of the day compared with the rest of the seasons of the year. The peak probability of thunder in the region during those months is in the afternoon, which is what we would expect from what we've already seen. And there's a similar but less pronounced trend in that diurnal signal towards the end of the monsoon into the fall. Interestingly, the line for the spring months and the pre-monsoon has in the mean for the whole region, there is a slight shift of the timing of this convection to a little bit later in the day, which it doesn't look like much on this graph, but that is probably a signal from mesoscale trends like those nocturnal MCSs kind of bumping the mean in another direction. And then when we look at the timing of peak probabilities versus an elevation map of the region, we can see some that according to this left-hand figure, which is the color-filled time of maximum thunder hours probability for the entire year. This could easily be done for different months of the year, but we chose to look at just the large-scale view of it for now. Most of the thunder in the daytime most of the observations of thunder that are the most common in the region happen during the daytime hours and into the late afternoon and evening. You do see some of those afternoon and evening storms. It might be a little hard to read, but here over the Deccan Plateau, representing some orographic lift of the winds that come in off of the oceans that then force convection there. We also see this nocturnal maximum that's very stark over the Himalayan foothills, which is, again, this whole area has been documented to experience a lot of nocturnal MCSs at different parts of the year. And then there's also this daytime peak in the Himalayan highlands, which is very easy to pick out in the animation, even if it is less obvious here, since the rest of the region experiences a lot of daytime storms. And then I had this color-filled elevation plot next to it for partly my own reference, but if you kind of line up where you see these features, it stands out very starkly with where there is higher elevation regions that can help force that convection. In summary, thunder hours are a powerful tool for visualizing and studying synoptic lightning meteorology and climatology. They reveal diurnal trends in lightning as well as monthly and seasonal trends. They're resistant to flash density bias caused by a few strong storms that may not have happened in another year. And they are also resistant to changes and inconsistencies in detection efficiency of a lightning location network. The 5-year thunder hour climatology accurately captures convective patterns associated with premonsoonal and monsoonal convection, which have been documented in past literature. It also highlights the frequent storm activity over the Deccan Plateau, along the coastlines, in the northern plains, and along the Himalayas during these months. Diurnal and sensible heating effects, as well as orographic forcings, are observed as they shift and change during the year when the large-scale flow shifts and changes throughout the year. This analysis really just scratches the surface. We at Earth Networks are encouraging researchers to make use of the Thunder Hours dataset and identify features and patterns that we haven't discovered yet. We're currently working on actually making this Thunder Hours dataset publicly available for broad research around the world, pending publication of the dataset in a peer-reviewed journal, which is my current primary project. If you're interested in using these data, please feel free to contact us authors, me, Mike, and Jeff. We're the research and development team at Earth Networks. We are really interested in sharing this with the research community as a whole. And with that, I will take any questions.
Thank you very much, Elizabeth. I think very interesting data set. And as you said in your conclusion, we have barely touched the surface of this whole thing. And it's very interesting for the region, particularly. So since we have time, and Elizabeth, thanks for finishing well in time. So any questions? I notice about 27 participants are logged in. So please.
Sir, respected chair, may I ask
identify yourself.
Yeah.
Sir, please,
may I ask
go
a question,
on.
please, sir?
Just identify yourself. Identify yourself and ask.
Okay, I am Dr. Mohan Kumar Das, working as the Executive Director of National Oceanographic and Maritime Institute. It is in Bangladesh. Just the presentation is really so nice. Lots of interesting things are there, and there is a lots of scope for further research. As presenter mentioned, the data is, I think, freely available. Maybe need some communication. Just a small query regarding the diurnal seasonal trends. So in the slide, it is mentioned 3 months interval. But in Indian subcontinent, it is usually considered monsoon is a June, July, and June, July, August, and September. 4 month interval. So which may be one query. Regarding that, it is very interesting. So I would like to thanks to the presenter. Thank you very much, respected chair.
Thank you, Mohan Kumar. For Elizabeth, please.
Yes, thank you very much for the feedback. For our publication, I could pretty easily change that designation in that analysis and rerun it for capturing the full monsoon season correctly. Thank you.
Thank you, Elizabeth. Any other questions? So, Elizabeth, I have a question about, this data is entirely captured from the Earth Network's observational points?
That is correct.
Okay.
Earth Networks and Woolen combined, okay, but we're, okay. Yeah.
Yeah, we are actually, I'm from an organization called RIMES, as was when I was introduced. It's a regional organization, and we work a lot on disaster early warning systems. And we, in fact, in one of the states in India, Odisha, where we are working with the Disaster Management Authority, we are, getting the Earth Network's data into the system. And it's currently, so my other question is, did you try to cross-check it with any other, NWP products or anything else coming out of the models or something?
Not yet. My primary focus has been on preparing the lightning-related, Thunder Hours data set for publication. Most of the knowledge that I've been trying to glean on the patterns that I see in this have been based on literature review. So I have some plans to try and look at model reanalysis data compared with these trends. My PhD is from a meteorological background, so there have been already a lot of things that I've been able to see in this data set, which my co-authors, who are primarily lightning physicists, did not see. So I think that comparing this with reanalysis data would be very useful. I also think that it will lend some more insight into regional patterns that are seen in this.
Thank you very much. I think very interesting work. And once again, are there any questions from the participants at this point? Okay. If there are none, thank you, Elizabeth, for your very nice presentation and very interesting introduction to this rich data set. Thank you.
Thank you very much.
So then we'll go to the next presentation now. We have Nachiketa from IRI Columbia joining, and he's a familiar face to me, and we have been meeting often in the SASCOF South Asian Climate Outlook Forum. So the next presentation, which he's going to make, is on next generation seasonal prediction systems for Bangladesh. Over to you, Nachiketa. And
Thank
a
you,
pleasure
Dr.
to see
Srini.
you.
Yeah, same here. I have some technical issue earlier. I'm trying to share my screen. Please let me know if you can see my presentation. Can you see my presentation?
Yeah, we can see the presentation now, Nachiketa. I hope everyone else is also.
Yeah, I had some technical issue earlier. That's what I did not connect earlier. So
Yeah, it is all right. You can see.
Okay.
Okay. Thank you. Thank you, Dr. Srini, and thanks Saurabh and others from the Dhaka University to give this opportunity for us to present our work. So this is a work which is done by International Research Institute, Climate and Society from Columbia University, Bangladesh Meteorological Department, and CIMIT Bangladesh. So this is I'm going to talk about a new product which BMD started, I think since last winter, and it's called Next Generation Seasonal Prediction. So let's start, and just to give the background, like why we need this next generation and what does it mean. So as Dr. Srini mentioned, that in different Climate Outlook Forum, we meet together and we talk with the scientists from the National Met Department and WMOs, and we are talking about to have a system where the forecast system, especially the seasonal forecast system, should be in objective mode. That means it can be traceable, it can be reproducible, and it can be well documented. Because most of the cases, like national met agencies, they make the forecast using a subjective consensus. That means looking at different forecasts from different leading centers like ECMWF or IRI or APCC, then make some kind of a mental combination and make a forecast. But WM is promoting this thing, I think, last 4 or 5 years, to have a objective consensus forecast which can be calibrated and combine all the state of our climate models. So that's the reason that we are working on that. And thing is, like, where you can find, those who are not familiar with where you can find from the this product in BMD side. So just to give you a little quick video, you can just go to the BMD website, and in left panel you can see a tab called Next Gen PyCPT forecast, and you can see that forecast, and it's there from last November. So this is like, I'm talking about this product and how we generated and what are the steps behind those products. So now question is, how? So like, how we make this forecast? So first of all, this is like this have a different steps. So first of all, already like obviously the research, but the important thing is like capacity building of BMD by IRI through different projects and different platform. So we actually have a recently, like last 3-4 years, we have a different project. One of them is Climate Service for Resilient Development in South Asia, funded by USAID. And currently we have a Columbia University's own world project called Adapting Agriculture to Climate Today and Tomorrow. And through this project, we have like several trainings, like, at least I did like at least 4 or 5 training before that, Simon Mason and others like involving. So it's not like, just, implement the system. It's actually to understand the system and make it standalone, that BMD can make their own forecast without any help. So that's what like it's a go through a several training with all the great scientists at BMD, like Manan, Kamrul, Rajia, Bajrul, like so many people are involved on that. It's not like a one person things. Uh, so now I'm talking about a little bit of science, like, okay, what does it mean by and how we conceptualize this forecast? So first of all, this is based on the climate models. But as we know, the climate models itself has lots of limitations. It's based on different assumptions. So we cannot just use the raw model output. So we need to correct it. We call it calibration. So in this flowchart diagram, you can see like we correct each GCMs independently with the observation. And then we do the skill assessment following all WMO's guidelines, like what are the skill metrics we should use. And then we make the calibrated multi-model ensemble based on the best selected models. And then we make the skill assessment of that final product and make the operational forecast. So this is like a whole system. And the important thing is like observation, because as you know, like climate model comes in a graded product, like every grid you have a observation, but for BMD, we have a station data at, I think 37 or 39. So instead of downscaling that climate model for each station, we try to develop a new data set. And actually the motivation of that data set is not only not only the forecasting, is also to use that high resolution graded data set for other application, just like agriculture and hydrology. So a little bit of that. It's actually a 5 kilometer resolution data. It has several steps, like it starts with downscaling, bias correction, and merging. It's actually a merging between a station data from PMD and the satellite product. And that data available for daily, decadal, like 10 days, monthly. And it started from 1981 and currently available, like updated every month by the excellent team in BMD, Bajrul and Rajia. So this is an example like how like the philosophy, how we make this data. So left panel is like a station data and right is like satellite product. Right now we are using chirp for station for rainfall. And then we just adjust using several steps, and then we merge the final product. Same thing for temperature, but for that we use the Japanese reanalysis data, GRA, and then do the same thing. So, and the important thing is this data is available freely for the public, and thanks to director of BMD, uh, like approved for that. So again, I'm just showing a little video where you can find, just go there and you have like all the data updated, and it's amazing. Like, we can just play so many things with that data. And another thing we also develop, like, sometime what happened for the non-climate scientist, like, okay, so we provide the data, but to process the data, they need to do so many things. They have to learn so many things. So that's what we also prepare. We call a map room. So again, if you go to the climate data library in the BMD data set, you can go to the BMD map room. And in the climate, you can find different like tab, like climate analysis, like monitoring. So I just give you one example of, if you want to see the seasonal climate analysis, how the season look like, and if you want to change the data, time period, rainfall to temperature, max, mean, you can do anything. Also, the important thing is like climate monitoring. You can just have a like almost real-time data, real-time monitoring of the drought. So these are example of real-time monitoring of the data. Is actually, it's updated I think up to last month. So this is like amazing, like, so instead of just downloading the data and start from the scratch, you can just do like lots of things and having the information for your work. So yeah, so now coming to the GCM. So what are the GCMs we are using? We are mostly using the state-of-art North American multi-model ensemble data set. The reason behind using that data set, first of all, they have a long time series, like they have a hindcast or past forecast from 1981, as well as they are like updated every month on 5th. So they are available in the real time. and these are all also free, and we can actually, IRI is a proud host of those data. So we actually using IRI data library to host those data, and very easy to download, and it's very up to date, and they follow some kind of common norm. For example, making the forecast in 1 degree and using the same kind of initial condition for each like month. So it's a very consistent, so we can actually combine this model. So now the question is like calibration. So we explain the observation is NXBD, BMD data is from GCM, but how we calibrate. So we are actually using the canonical correlation analysis, which is a multivariate statistical analysis. Basically, instead of just having the regression between GCM and observation, try to regress between the highly correlated empirical orthogonal function between GCM and observation. Just give one example. Like this is like when I say UA for principal component, this is nothing but like the prominent pattern of the data. So this is like one example of observation. The prominent pattern look mostly positive from the first, and the second has like some dipole between north and south. So this is one example of some GCMs. So we are like actually input of this system is those UF, then this system calculate the highly correlated those UF or canonical variates, and then do the linear regression, and then reconstruct it using that inverse of the UF. So this is like a very common and like popular method. So we need tool for that. So we are actually like, maybe who are familiar with the IRI, they also familiar with the tool called climate predictability tool. This is a very famous tool, and we are using it. Most of the researchers from this area, they are using it, but it has to be using for a different kind of forecast, like where people are trying to make a forecast based on teleconnection. For example, you have the rainfall of the Bangladesh, and you're trying to find out the best predictor in somewhere in the Pacific or Indian Ocean, and then make some correlation based forecast. And people are using CPT for that. But for this particular exercise, we are using CPT, but in a different aspect. We call model output statistics. So instead of like SST and rainfall, we are using climate model output rainfall, and the observed rainfall as a predictor and predictant, and then we actually doing this CCA and make this forecast. But it has some limitation because, as I have shown, like we have so many models, so you have to run this window-based software CPT like several times, which is a very tedious, especially like when we are using in a real-time forecast. So for that, we need some kind of a system where we can run CPT multiple times, and we can also generate all the plots. So that's what we are trying to make a new system called PyCPT, or Python script to run CPT. Is actually a Python wrapper, like just inside the CPT. So we are still using the CPT as a core, but we are using Python as a script function to run it, to call it multiple times and in a single changes. So basically, it is start with the changing the name list, and then downloading the data, then forecast skill assessment, and the forecast. So where you can find, so again, like in our web page, in the tools, you can find the CPT. In the same way, you can just get a link for the PyCPT, and if you click there, you can ended up with this kind of map, which is we put in a Bitbucket. So the important thing is like PyCPT is still on, like we are developing this thing from a year from now, and we are keep on updating this system based on the user feedbacks, and we got lots of feedback from BMD itself. So the first version of PyCPT was totally different. Now we have a very advanced, thanks to BMD scientists to give those inputs. So it's again freely available. Anybody can download it, and it's very easy to run. And we have some tutorial over there. So now I can show you like, okay, this is the system, these are the tool, but what the skill of that forecast? So just one example, obviously, like we're talking about Bangladesh, so the evaluation should be on the summer monsoon. So for this exercise, I just took up time period from 1982 to 2018, and using all available operational GCM from NMME, and using a May start JJs. That means like lead one forecast, like every model predict June to September in May. And then we compare different kind of skill score, like what is the skill of before, like raw models compared to calibrated models, raw models multimodal compared to calibrated multimodals. So this example, like this, I just took a 3 random model. One is from GFDL, one is from NASA, and one is from NCEF. So this is the skill of the raw models, and we explain this skill in a root mean square error, which is millimeter, and the Spearman rank correlation, and the generalized discriminant score. So this score is little different, which tell us like how forecast is efficient to discriminate between different uh, episodes. So just show you like how much we gain after the calibration. So if you look the the range of the root mean square error for each model, it is very high all over the country, especially where we expect more rainfall in the northeastern part and the southeastern part. But actually, like when you calibrate it, like we have like a very less compared to the raw model error. Also, we improve a lot in terms of correlation. If you look, in CFS, like CFS has some skill in the north, but it's mostly like no skill over the other part of the country, and we improve a lot, especially with the NASA model. And this particular skill score telling us like how much our focus is actually discriminate between below normal and above normal years, and anything greater than 50% is actually we kind of discriminate this forecast in different events more. So in that case, like it's also improved. So it's very important, like this the reason behind I showing this slide, like so important to use calibration instead of just using the climate models. So now coming to the multi-model, like again, this is like uncalibrated and this is calibrated. You can see the huge improvement of the scale in terms of the error, in terms of the correlation, and in terms of the discriminant. So this is like a state of art. So doing this exercise, we are trying to find different skill score of different models and combine the final forecast, which is CMME, and then make the forecast. So now the skill is for like I show is like from 1982 to 2018. But what is the skill in the real time? So as I said, like since November 2019, BMD started this forecast. So we have only one monsoon, which is this year. And we all know like this year monsoon is like really very anomalous, having a huge rainfall. So this is a example, and thanks to Raji and Kamru to make this plot in real time, and thanks to share with me. So this is like a forecast in May start, JJS, and this is I, if you can look that bar, it's like up to like 5,000 millimeter in a season. So, and this is like the enacts observation, and they look like very similar. Like when they plot, we thought like maybe there's some mistake, like maybe it looks same, but it's actually different. Two different models, sorry, two different data set, but it looks so similar. And the pattern, like mostly the northern part and the northeastern part and the southeastern part are having a huge rainfall this season compared to the other part, and it's captured. And we also like break it because this system in BMD is actually making the forecast for every month for next season, which is 3-month average. So this is the real time in the May. So when they make this forecast in May, like we are kind of not so much confident because we don't know whether this year monsoon will be very havoc or not, but it's actually happened. This is the observation. And same thing for the JS. In fact, JS, like July, August, September, has more like magnitude wise more rainfall compared to the other season, and this forecast also captured but little bit of difference. And we are trying to right now to look this forecast product in a different way, making a climatology, making anomaly, making a different category. So we'll do more diagnostic on this real time, but this is like a first scratch plot, and we found excellent, like this system captured this particular this year monsoon, as I said, is very anomalous, so it's captured this thing. So now one more thing, like this is like a static map I show up to now, but now we also develop an interactive user-friendly map room based on the forecast. Again, like if you go to the Climatology library and same way, like go to the BMD map room and climate, and you can also find a tab called climate forecast, and there we can find the next gen forecast system. So this is a very interactive map room. So this is like the map, like the total rainfall, which is almost same like the static map. But if you want to see the what is the anomaly, so you can just change the field from rainfall to anomaly, and then you can actually get the plot, which is telling you how much it is above or normal compared to the climatology. Same as you can make like a tercile probability map, like what is the 3-category probability map for that region, like below, above, and normal. And the important part is like this, the probability of accidents. For example, if you're interested to know the probability of some threshold, let's say I put here around like 250. So if you put that value, any value, click there, it's automatically calculate the probability which is exceeding the 250 millimeter rainfall all over the Bangladesh, and you can get that the distribution. You can also change from the rainfall amount to the percentile. Like if you know like what is percentile, like percentile telling us the data, like is actually sorted the data based on different
Niketa, you have a couple of minutes.
categories. So this is a median. Yeah, I'm almost, it's my last slide. Okay, so this is like one example of 85 percentile. So after that, like, this is like a very informative for the user point of view. And again, like our collaboration started from last like 2-3 years, but we're still working on that. And especially this COVID-19 time, we have several online things. And I just want to mention one thing. Recently, there is a WMO bulletin in this month, in November, sorry, last month, and where we particularly refer this thing, and they actually encourage BMD to working with this in compound risks time where COVID and the Amphan, and they encourage IRI to help on that. So in that way, I just want to say, like, it's an excellent product, and I encourage people to use it. And we are also planning to include more variable like temperature, and also like more different kind of forecast like subseasonal forecast very soon in BMD. And thank you very much. And please give your comments and feedbacks. Thank you.
Thank you. Thank you very much, Nachiketa. And sorry to have rushed you a little bit at the end, but I think it's a very interesting and very nice improvement in the tool. Are you able to hear me? There seems to be an internet problem, but yeah, I will try to go on. So before I open the floor for question, I see Mohan Kumar, you have raised your hand. But before that, let's welcome my co-chair has joined, Professor Zillur Rahman. He has just joined, and if you want to say something, co-chair, please go ahead. Otherwise, we can open the floor for questions. Thank you.
I'll tell later. Thank you very much for
Thank you. Thank you, Professor.
Okay, we can continue with the question later. I will tell you.
Yeah. Okay. Over to you, Mohan, for your first question. Mohan, your mic is muted.
Okay, sir. Sorry, there is some internet connectivity problem. Are you listening me, sir?
Now
Yes.
we are listening. Yeah, Nachi is there to
Okay,
answer.
thank you, sir. Very simple two queries. Very nice presentation. Actually, now we are doing some weather insurance training, which is conducted by IRI. So actually, same thing what Nachiketa already shown. This tool we are using. Very interesting. So one small query regarding the bias correction. What kind of bias correction methods is applied in the study? That's a small query. And another is there is a very limited extension in Bangladesh. So how this limitation is considered in the further study? Thank you very much. Thank you, Nachiketa ji. Very nice talk. Thank you.
Okay, thanks, Mohan. Yeah, so as I explained, maybe I was a little rushed. We are using a canonical correlation analysis-based regression. The philosophy is like try to capture the spatial pattern from the observation and implement it in the model to correct the spatial errors. So that's the method we are using. Coming back to the station, as I mentioned, that we are using the gridded data set based on this station and merging the station of satellite data. So yeah, we know there's like a less station like 37, 39, but we still like that's what like we are using the satellite data. And I think like, we also compare, like there's 3 paper on the way, and when it's come, I can share with you, like where you actually compare different intense rainfall active like events and the overall climatology based on each station data compared to other products. And this product, especially that Enax one, is really very interesting and excellent performance. So I think it's okay, but in future, whenever BMD increase more station, we can just easily incorporate in the system. Thank you.
Thank you. Thank you very much.
Thank you, Nachiketa. Any other questions? We may have time for just one more question. So if there are no questions, Nachiketa, I have one question before we say bye to you. I mean, one of the slides which you showed, the 2020 prediction was particularly very, very striking. So what was the larger scale prediction over the region also similarly very nicely brought out, or what was the reason?
Are you talking about IRI's forecast on the larger region?
Yes.
Oh, yeah. So this product particularly on the Bangladesh. Yes, I think like I'm going to show in the next ASCOF on that. So we are surprisingly like get that kind of skill because in April onwards, the all model shows a like a probability of heavy rainfall in the southern part of India, and we are kind of a little doubtful because that part is not like it's mostly for the Tamil Nadu. It's like always a rain shade area, but this time like lots of activity over the Bay of Bengal actually bring that much of rainfall, and mostly like all over like including India, Pakistan, Myanmar, those every area like the forecast is very good, and it's because of the La Nina, because most of the models capture this La Nina very early, and that happened this year. So that's what like model performance is very good. So I'll share the quick skill of the IRA forecast in this 2020 with you.
Thank you, Nachi. That was a very interesting slide which you showed on Bangladesh. Yeah, that's why I thought maybe the larger region also has some
Yeah,
signal
we
was very
captured
strong.
this thing.
Thank you. Now let's move quickly to the next presentation. This presentation is from Paul Kucera from the UCAR. He is going to present on the low-cost observational network to support agriculture and hydromet applications. So over to you, Paul. Thank you for joining.
Thank you. Can you see my presentation?
Yes, we can see. We can see your presentation.
Okay, great. Thank you. Yes, thanks to everyone for having us be able to present today at the conference. And good evening to most of you, and good morning to some of us here in the United States. So yeah, for this presentation, I would like to talk a little bit about our innovative technology that we've developed to help improve observations for various applications such as agriculture and hydrometeorology applications. So, this project was originally funded by USAID and the National Weather Service in the United States to build capacity in developing regions. Whoops. So yeah, the technology that we've developed is what we call as a 3D printed automatic weather station, or 3D PAWS for short. This initiative was developed and launched in 2014 with the goal of reducing disaster risk reduction in various nations. The goal is to design and implement a sustainable observation capacity network in least developed data sparse regions to supplement areas where there's very few observations. And this provides early warning observation capacity to reduce risk to vulnerable communities. And the whole idea is to provide this a low cost and innovative solution to support weather related activities. So how is this done? We use 3D printers, which these days are very relatively inexpensive. You can get a 3D printer on the order of a few $100 US to $1,000 US, and you can print multiple stations of that. We integrate these sensors into the 3D printed housing using these low-cost microsensors. And then the whole idea of our project is designed so that the stations can be built, so fabricated and assembled locally. And the nice thing about this technology is when components fail, and as every instrument does, various components, sensors fail or break or get stolen or whatever, you can print and replace the different components to keep your system up and running with little downtime as possible. So this enables local agencies to really take ownership in building this and maintaining their own networks instead of requiring to have stations come into country. The picture I have here is just a showing of a very typical setup of our stations, which in this case is located in the country of Uganda. The station, just kind of some of the details of the station itself. We use, if you might be familiar with a single board computer, Raspberry Pis, very powerful, inexpensive systems that do all the data collection, data processing, and then support the transmission of the data to a data server in real time. And then we've developed a 3-cup anemometer for measuring wind speed, a wind vane for measuring wind direction. We have a light sensor that measures incoming infrared invisible light, and then also calculates UV light. And then we also have a tipping bucket rain gauge, which is shown on the bottom here, so it's able to measure rainfall rate at a resolution of 0.2 millimeters per tip. So you can measure very high rainfall rates with this system. In our ventilated radiation shield, we have currently 3 different types of sensors. We're currently measuring temperature. Actually, each sensor has a temperature measurement on it, so we have three measurements of temperature for intercomparison, consistency, and for data quality control. We also measure station pressure to compute atmospheric pressure at the surface, and then we also observe relative humidity at the surface. We've designed the system to be very, very flexible, such that you can have a wide variety of different power and communication solutions on the system. So most stations we install in remote regions, which are powered by a solar panel with a battery backup, which keeps the stations going. And we normally measure make measurements right now, the default is every minute, and that minute data gets sent to a server that you can then see through a web application in real time. In terms of communications, there's a variety of options available. If you're in a lot of our stations, we've partnered with schools, and so the schools have wireless communication, so we can go into their wireless network, but most stations are tap into the cell phone network of the region. We can also do satellite communications through Iridium or geostationary satellites such as Meteosat. And we're now working on low-powered, long-range solutions called LoRa, which can then transmit on their own internal networks to a central data server. If you're wondering, the cost of one of these stations to produce is about $300 US for all the different components. That includes all the printing components, the sensors, the frame, everything else. So it's a very low cost solution. And it takes on the order of about 1 week to print one station per printer. We're also, based on a lot of the feedback in our development, we're also developing a variety of new sensors to help with the systems. So in terms of new sensor development, we've developed a stream gauge. This gauge is able to measure stage height. So looking at monitoring either in irrigation ditches or in rivers for possibility of flooding. We're currently working on stream flow, so you can actually get flow rates to measure the amount of water, and help with either water management or monitoring for flash floods, things like this. Agriculture applications, we've developed a soil and temperature sensor to monitor the ground conditions for farming applications, such as when to plant, when to harvest, fertilization, things like that. We're currently working on an air quality sensor package, especially for areas around where there's a lot of air quality issues, such as in large cities. So looking at particulate matter observations, ozone, VOCs, nitric oxide, and other constituents like that. And that's an ongoing process. And then lastly, we're working on is a local lightning detection that can then, if you put these together in your surface observation network, you can then also monitor the local lightning in your region for severe weather if you have no other observations available. So in terms of our where we're at in terms of the status, we've been, like I mentioned, we've been working on this project since almost 6 years now. Our current, as I mentioned, our current station measures the state variables: temperature, humidity, pressure, light, wind speed, wind direction, and rainfall. We're currently in 11 countries. We first started our network in the country of Zambia in Africa and spread out to Uganda and Kenya. We're in the Caribbean, in Turkey, a few stations in Europe. What's exciting is that working with the University of Dhaka, we're planning our next implementation in Bangladesh as soon as we can. We're able to travel and do the training with the university and get started on building a network in Bangladesh. So, and part of that is we do extensive training. Again, our whole goal is to build the capacity in country. So in training, set up a fabrication facility and teach our partners how to make them. And we're in partnership with the World Meteorological Organization. They're very supportive of this innovative technology, working with universities, National Met Services, education outreach, Globe, for example, and then primary and secondary schools, which are a lot of times the host and take care of the stations. In terms of the training that we do, it goes through the whole process, through the 3D printing process itself, how to fabricate and assemble. We teach our partners how to install and maintain the systems as any instrument needs continuous maintenance. And then assist with application development. What kind of tools can you use to with the data for decision support? And here's just a example of the different setups in different parts in different countries. So the one in Barbados, Uganda, Vienna, and Kenya. I failed to mention that there's about 60 stations up and running around the world as we speak. So in terms of application support, there's a lot of use for having this high resolution, low cost data. One is input data assimilation into weather forecast models, where we're currently working on a pilot project over the Lake Victoria in Africa to ingest the observations to improve on short-term forecast for early morning of high impact events, thunderstorms in the lake, and so on. With that, we'll build in early warning systems, provide that information to users, stakeholders on the ground, such as flash flooding, severe weather, high winds, and things like that. And then also other applications, engineering support, such as water resource management for managing reservoirs and dams. I mentioned agriculture applications, another important aspect of using the observations. So yeah, I mentioned this already, but what we're doing is focusing on improving weather forecasts through data assimilation, using regional weather prediction model, in this case, the weather research forecast model, WRF, that was developed here at NCAR. Working on the data assimilation framework, so it's easy to ingest these data. And then, again, I mentioned we're using the observations to improve warning of high impact weather events. Another example in terms of flood and agriculture monitoring, the water level gauge has been developed for stream level, irrigation, storm surge. Another thing that we've done, we've teamed up with the National Hurricane Center in the United States to put these gauges along along shorelines, so we can monitor storm surges associated with tropical storms to provide early warning and also verification of storm surge prediction models in this case. And as I mentioned, the soil moisture temperature sensor used for agriculture applications such as irrigation and crop monitoring. And then just wanted to highlight that this is truly an open source project. So if people are interested in developing their own localized, low cost innovative network like 3D-PAS, we have this is our project website. You can go here and learn more information about how to actually get started on building these stations. So with that, I'll stop and say thanks for letting me present this today, and I'll be open for any questions. So thank you.
Thank you, Paul. Thank you. I think it was really amazing, work on this very important problem for the region as well as the globe. As you said, many countries are already in the process. So I'm sure there will be some questions. So let me request participants to raise their questions, if any. So I think most of us are amazed by this technology, Paul.
Oh, thank you.
So I think, how does the technology transfer actually work? You showed us some slides about, training which was conducted. So is it transferred to a Met service or some agency which requests such a thing to be there on an ongoing basis? Thank you.
Yeah, it's actually really dependent on our colleagues. So we've worked closely with Met Services, for example, in Barbados. They are manufacturing all their own stations now, and they plan to install on the order of 100 stations for really high resolution monitoring for severe impact events. We've also worked with universities, like we're going to be working with University of Dhaka to install a fabrication facility there and get the students involved in the training to really build that capacity. And then we're also working, as I mentioned, with like Globe to help with bringing the stations to schools and teachers and students to really learn about their local environment. So it kind of depends on the interest and the partners. So yeah, it's kind of a variety. So it's actually really exciting mix of groups we work with.
Thank you, Paul. I see that you have another presentation also later after this one. So we will hear you again. So thank you very much for that, sharing that great work. Thank you.
Thank you.
So we will move to the next presentation, which is going to be given by Elizabeth Page from UCAR again on COMET training resources for developing advanced weather forecasting expertise. Over to you, Elizabeth. Thank you.
Thank you very much. Can everyone see my screen?
Yes, we can, Elizabeth. Go on.
Sorry, and I will present. Okay, everyone can see all right?
Yes, we can see all right, Elizabeth. Go on.
Thank you very much. All right, thank you everyone for staying on so late. For those of you who are in Bangladesh and surrounding areas, I appreciate the accommodation that the organizers of the conference have given us to be able to present during our time zone, which is morning for us in Boulder. And I greet you from Boulder, Colorado. We have had snow overnight, so we have a light dusting of snow on the ground right now. I am here to talk about COMET training resources for developing advanced weather forecasting expertise. My name is Elizabeth Page. I am the director of the COMET program, and I'd like to acknowledge my co-author, Paul Kuchera, who just spoke and will be speaking after me. Obviously, he's been very busy. Just a quick overview of what I'd like to talk about this morning, mostly about our MedEd website, which is our training portal where we deliver all of the online training that we develop at the COMET program. COMET has been around now for 30 years, and we were originally created with funding from the National Weather Service in the United States to train forecasters on Doppler radar interpretation. Doppler radars were at that time being deployed around the US, and forecasters did not have that background. They had not had that training either in their college courses or in training from the Weather Service. So this was a new topic, and we were developed to do distance learning, meaning that we were bringing the training to the offices and to the forecasters in their offices rather than having them travel to in-person training. So as you can imagine, with COVID-19, we have seen a great increase in the amount of training being delivered from our MedEd website. Obviously, it's very popular for professors who are teaching remotely now and needing some support materials to help with that teaching. So I'd also like to talk a little bit about our training development model, recent training topics that we have published, some of the simulations that we are working on within our individual lessons, as well as some gaming techniques that we're starting to employ. I'd also like to talk a little bit about our translations. COMET modules, not all of them, but some of them are available in 8 different languages. And we have a full-time translator who is a Spanish speaker, but also facilitates translations into other languages. And then finally, I just want to talk a little bit about our training development resources to help people who are trying to do their own distance learning development. So turning to MedEd, again, MedEd is the portal of our training resources. I have the URL here at the bottom of the slide, just www.meded.ucar.edu. It is a free registration system. You do have to register in order to access the training on the site, but it is free of charge. The system is up 24 hours a day, 7 days a week, so you can access it anywhere in the world, any time of day. We also track progress through the modules. We have quizzes for our lessons, and as you pass a quiz, it is put into your transcript on the system, and also you receive a certificate for that lesson. We have review ratings available. We have a survey that you can fill out after the course is completed. And we also have a 5-star rating that can be done outside of the actual course. We also provide access to all the graphics and animations in the courses. They are available free of charge. Our reuse policy is very broad. We grant reuse privilege for anyone doing non-commercial educational work. So if you are a professor and you would like to include our graphics in your lectures, you are completely able to do so. You can just download the graphics from the site and put them in your PowerPoint presentations or Google Slides or whatever method that you use to teach. We also have in the registration system the opportunity for people to share the scores on their quizzes, to share the accomplishments that they have made. So again, if you are a professor, you can assign these modules. The students can put your email address in their registration, and when they complete a course and pass a quiz, you receive an email with their passing score. So we try to make it as easy as possible for reuse of these lessons in the classroom. Some of our recent training topics that we have published this year include a 10-module, 10-lesson course on instrumentation. And
Sorry,
the example that we show right here. Hello?
Elizabeth, your
Yes.
slides are just frozen on the first slide, actually.
Oh no.
Yeah,
Oh, no.
we thought that maybe you're just giving a very detailed introduction.
A very long overview.
So sorry, I should have
4.
stopped it actually. One of the organizers just put a chat message. Please check.
Oh, I'm sorry, and I don't have my chat open. I'm sorry about that. Okay, let me try just sharing it rather than present from the actual slides. So are you Are you seeing the PowerPoint presentation?
Now we are on the recent training topics. Yes.
Yeah.
Yes. Okay, great. All right. Thank you. I
Now we are
apologize
all
for that.
set. We are all set. Thank you.
So,
Would you please do the full
slide number 2 and 3 weren't that exciting.
Would you please
right.
present the full screen? Full screen.
The full screen. Oh, absolutely. Okay.
Can you go to the slideshow? They want you to slideshow.
Okay. Let's see if this will work again. Okay, so now you are seeing the slide on recent training topics?
Yes, we are.
Training topic, yeah.
Wonderful. Okay. Thank you. I'll let you know when I go to the next slide and you can tell me whether it comes up or not. All right, so as I was saying, the recent training topics that we've been covering include a 10-lesson instrumentation course on measuring atmospheric parameters. And this course has, again, 10 different lessons and they're on different types of measurement. So in the, as you can see from the thumbnail of this, the instrumentation and measurement of surface precipitation, we have the, the very fundamental atmospheric parameters that you would measure, such as pressure, precipitation, cloud cover, that type of thing. And each has its own module. It was developed in partnership with the Earth Observing Laboratory at the National Center for Atmospheric Research, which again is part of UCAR, which is what we are part of, and Millersville University in the United States. So again, if you're interested, if you're a teaching instrumentation course, this might be nice supplemental material for you to use. And again, the graphics that are available may also be helpful for lectures that you are putting together. Another area that we have been working with, this is with the National Geospatial Service in the US, are part of the National Ocean Service as a government agency, and it's geospatial topics. So these deal with anything from datums to how you measure sea level. There's various different lessons that are available on those topics. And for instance, we have this GNS positioning, survey planning, and data acquisition. So if you are teaching courses related to measuring sea level height or other things related to geodesy, then there's a whole group of lessons that you could use to support that. One of the other topics that we've been updating this year is our rip currents module, which is a huge hazard in the United States as well as other coastal areas around the world. And this has some very basic concepts related to rip current development that may be of interest. We continue with our satellite applications in the United States. We've had 2 new groups of satellites, including our geospatial satellites, the GOES satellites, and also JPSS, which is our polar orbiting satellites. So our training related to the satellite data now is based on applications. And we have produced several modules which integrate the geostationary and the polar orbiting satellites for different types of weather. And the example that I show here is the assessing convective initiation with these different satellite data and using them together. Another topic that we are working on, this is a new push in weather forecasting. So these courses are geared towards weather forecasters who are moving towards impact-based forecasting. This is in the US, we also call this integrated decision support. Basically, this is forecasting while taking into account the impacts that the weather events will have on the people, on your audience, basically on the stakeholders for the forecast. So we have a series of impact-based forecasting modules. The one that I'm showing here is the communication of risk. This is impact-based forecast watches and warnings, and this uses a case study from Barbados in the Caribbean. And then the last topic I want to cover is the national blend of models in the US. We are looking at, rather than model of the day, which is the way we used to forecast when I was a forecaster, looking instead of how we can blend the models together to give the best possible numerical forecast for the forecasters. Okay, I'm now switching to the next slide. Can you see the next slide?
Not yet.
Okay.
Listen.
All right, so I think that maybe, oh, sharing is paused. How about now?
Now is okay. We are on simulations. Yes.
You can see the slide on branching simulations?
Yes, we can. Thank you.
Okay, great. All right, so one of the things that we are trying to incorporate into our lessons now, we have instructional designers that work with our team developing our training, and we are trying to customize the training for the learner. So with branching simulations, we ask a series of questions. As the learner answers a question, based on their answer, they will go through the module along a different path. So the idea is that if you answer a question incorrectly, it will take you down a path that will give you feedback on why your answer was incorrect, and also give you the opportunity to see what the impacts are of the wrong answer. So we use this a lot in our communication modules where we're communicating some type of forecast. And the example is, again, this communicating risk with impact-based forecasting. So if the forecaster answers a question and gives the person asking the question information that is not helpful to them, then the person gives the feedback to the learner that basically the information was not helpful. And in some cases, when you're in a situation or a case study, as we use in our lessons, where your answer has an impact on the lives of people and the decisions they make to protect their lives, then you can see that this gives us an opportunity to put learners in a situation where they can actually make mistakes and learn from them without actually impacting people. So that is the that is what we are trying to do with these simulations, and we are getting quite a bit of positive feedback from learners that these modules have been effective in terms of helping them try out these different types of approaches to different questions and having that feedback on when those answers aren't helpful. All right, I'm going to go to the next slide.
We are still on the simulation slide.
Sorry, I'm trying to go to the next slide. I'm not quite sure why this is so difficult. I'm going to stop sharing for a second and go to the next slide.
Yeah, now we are on the gaming techniques.
Okay. One of the other things that I wanted to share that we are now doing with our modules is to inject gaming techniques. And this example is from one of our fire weather modules, and it is using a Jeopardy game, which Jeopardy is a game show in the United States. I don't know if everyone is familiar. It's quite popular in the US, and it gives people an opportunity to answer questions on different topics. So in this example, we are using the Jeopardy game for what would be, frankly, rather boring topics to cover. And it's basically how a fire weather program is set up. So it talks about partners, policy, products, and people. And the learners learn the different content topics through answering these questions. So I encourage you to take a look at this if you're interested in that type of approach to training. This example is from the Navigating the National Weather Service Fire Weather Program. So I think you might find that interesting and fun to give it a try. Right. Are you seeing the next slide? Nope, wait, let me try.
No, I think we are still
Okay.
in the 5. Oh, yes, okay now.
The translations. All right,
Yes.
I apologize for these technical difficulties. At Comet, we translate many of our modules into different languages. We have a full-time translator. We have 9 languages. I think I said 8 languages earlier. And we have a translation resource center. So for people who are who would like to translate different training into another language, there is a translation guide that our translator has put together to help you think about some of the different things that you need to do when you're translating different lessons. And we also have partnership opportunities to work with our translator. If you're interested in translating any of our modules into a different language, we would be very happy to work with you. Our thoughts are that the learning process, the most difficult part of the learning process should be the content, should not be the language in which it's presented. All right, I'm going to attempt to go to the next slide.
I think the slide sharing has stopped, perhaps.
Yes, I'm going, sorry,
Okay.
That is me. Okay. Right, so this is going to be my last slide. I appreciate your patience with me as we work through this. Okay, then the final thing that I wanted to cover was our training development resources. With COVID-19, many universities have gone to virtual teaching and also training centers, the regional training centers with the WMO, and also different training centers at National Met Services have moved towards this distance learning approach. So we put together a webinar in March that was presented and is now available on our YouTube channel called How to Be Alone Together, Teaching Geosciences in Quarantine. It gives some ideas for how you can make online training more interactive, how you can engage the students, and how you can make it, therefore, a more effective training event for people. In addition, as you may know, most of our courses were developed with the idea of operational forecasters in mind. The training was developed as professional development for forecasters, but universities have found it very helpful in supplementing the training that they're doing, the teaching and education that they're doing in meteorology programs. So what we have most recently done with funding from the National Science Foundation in the US is to map our courses to the standard courses that are part of a meteorology curriculum. So far we have worked on dynamic meteorology and introduction to meteorology. We're also going to be including thermodynamics in this next round of our efforts. We are mapping individual modules and talking about which sections of the modules apply to these courses. And in the near future, sometime in the next couple of months, we will also have all the graphics associated with those modules then mapped to those courses as well. So it should streamline the incorporation of the materials that we've developed into these different course curricula. And again, this is all available free of charge. One of the other things that we have contributed to is an innovations in education publication that is actually 4 volumes. It was recently published by the WMO from the education and training group there. And I put a link to that in the presentation. And also COMET has a YouTube channel where we have educational videos that are available. And also we have taken excerpts of some of our more popular modules and made those available on video. For instance, we have an animation of the impacts of storm surge on coastal areas. And we also have an animation of the Safford-Simpson scale that shows the wind impacts due to tropical systems. So I think I'm going to end right there. I appreciate your patience as we move through the technical difficulties. I'm happy to take any questions. And again, I thank the organizers of the conference for allowing us to present. It's been a very good experience, and I look forward to be able to visit in Bangladesh again once we have made it through this pandemic. So thank you very much.
Thank you, Elizabeth, for despite the technical difficulties, it was quite interesting, and we are all very familiar with COMET and its resources, which we use very often. Any questions from the floor? Yeah, I think it is a bit late in the day for this part of the region.
I can imagine.
But yeah, as I said, COMET is very, it's one of the main resources for a lot of teaching programs within the Met Services, as well as many other institutions, I suppose. So we really appreciate the work, and we are very happy to see the new modules introduced, and also the new concepts being done. And particularly with this pandemic, it's become all the more important to have such resources.
Absolutely.
Thank you very much. So thank you. And we now go to the last presentation of this session. This is again to Paul Crescera, and he is going to speak on improving communications of impact-based forecasting systems. Over to you, Paul. Thank you.
All right, everybody can see my slides, I hope.
Yes, we can, Paul.
Great. Yes, yeah, thanks again for letting me speak for a second time here. And yeah, I want to talk about another project we're doing here in COMET, and that's in implementing impact-based forecasting for a variety of places around the world. So, so as an introduction, impact-based forecasting has been developed with strong support of the World Meteorological Organization and other member countries. They've published a very comprehensive guide. It's WMO number 1150 if you're interested. It's easy to find. It's also in the process of being updated for some new technology. And the whole idea of impact-based forecasting is to reorient the focus of what the weather will be. So instead of saying, oh, it's gonna be cloudy today with a chance of rain, but what will the weather do to society? What are the impacts to the people in your region? So will it cause traffic jams due to water on the road, things like this? So we've been working closely with WMO and our other partners to really promote this and get this out there to various countries. And as Liz mentioned, we've developed some training materials to help people get started with impact-based forecasting. So the whole idea, as I mentioned, is to move away from what the weather will be. For example, instead of just saying what the observations are or what the forecast may be, saying, for example, we're expecting 50 millimeters of rainfall in the next 24 hours with winds of 35 knots. So those are kind of the observations what the weather will be to what would be the impacts of those conditions of the weather. So, so you would communicate the information on what the weather will do, such as this will result in roads flooded in certain regions, communities be cut off because of, say, tree damage for high winds. Schools might need to be closed. There might be issues with emergency managers or say ambulance getting to hospitals. So providing that messaging on the impacts of what the weather will do so people can take action. So why is this important? As a lot of people know, a lot of stakeholders make decisions on the weather impacts on their activities. So for example, as I show in the picture here, depending on wind conditions, on their activities to go in fishing, impacts, say, to agriculture in terms of when to plant, go in the field if there's lightning predicted, severe weather, for example, keep people out of the fields for shelter. So there's a lot of information that can be conveyed to stakeholders based on the weather to make their decisions. So a lot of sectors use this information, such as fishing, as I mentioned, transportation, health sectors. So yeah, the forecasters can communicate this critical information on the impacts, such as emergency managers, transportation, say aviation, things like that. So it's an important partnership to work with weather forecasting and emergency management to communicate those impacts to society. So in terms of the value of impact-based forecasting, it improves the value of decision-making. It communicates the potential impacts of the forecasted weather. For example, Liz mentioned it's snowing at our place, so that's outside my house today. So in terms of impacting what weather is doing, this will result in slower drive times, dangerous roads. People need to stay off, as much as possible, stay off the roads to reduce the risk of accidents and so on. So if there was strong winds, could reduce the visibility due to the blowing snow and things like this, as an example. So the National Met Services work in close partnership with emergency management agencies and other stakeholders to convey this messaging to help people out on the ground. In terms of transitioning to a impact-based forecasting system, it really depends on an understanding of what are the hazards of the area, the vulnerabilities, and the exposures to society, and what are those risks of those weather impacts that could become human disasters. So what we want to do is identify, in terms of building an impact-based forecast system, you want to identify these different components and then build a system that can then communicate and message those weather impacts to reduce those risks to society. So I like to, again, use another example. Here's an example where the forecast forecaster could say we're expecting heavy rains of, say, 100 millimeters of rainfall in the next day over that region that's outlined in green here. So it's depending on if you can understand the quantification of what does 100 millimeters of rainfall mean to you, it might or may not make sense. So what does it mean for those people in the area in terms of warning? What should they do because of that potential of heavy rainfall? So you can move toward using what we call as a risk matrix, is to say, okay, instead of just telling you what the weather will be, is what are the impacts and what's the severity of impacts. So you can give information about what's the likelihood of that impact to that region, and in impact-based forecasting, it's done in a color coding system. So green, I always think is green is there's a low likelihood or impact, where red is a high impact, highly likelihood that people should take action. So in this case, in this example, maybe there's two regions for that same event. The green region on the outside, or I guess it's yellow, in this case, is a yellow warning. So there's a high likelihood of minor impacts in this case. So maybe there's some localized flooding on the roads. There could be some debris on the roads, maybe some minor landslides, for example. The orange warning, there's more of a significant impact, where there could be maybe bridges are closed due to flooding and things like this. So when developing a impact-based forecast system, there's a variety of steps that we take to help the stakeholders develop the system itself. So the first thing is you want to assess the risks of your region. And are those hazards known, and the vulnerabilities? Are the risks? Are there risk maps available? If not, where can you find that? Who can you partner with? What kind of information and data that can be available? And then the second step is developing the monitoring and early warning system. So are the right parameters being observed and monitored? And going back to my first presentation, if it's in a data sparse region, this could be a time where you can identify the needs for additional observations to supplement, so you have monitoring for this early warning. Can these messages be communicated timely, so that it gets out to the public, so they can take action before the hazard occurs, their impact occurs? And then developing a cohesive communication system. So working closely with the Met Services and emergency management to communicate those risks so they can reach the public. And developing messaging that's very clear and actual. So when you do the messaging, and the messaging communications can be through social media, it could be through radio, it could be through TV. It kind of depends on the region and how you develop your system, and then how it's communicated so that people take action and keep safe. And then the last step is building a national response capability, which means you want to do a lot of testing, a lot of training, as Liz talked about, are everything tested, and then building additional training material so people are prepared to react to these warnings. So I already showed this briefly in the example, but what comes up for each hazard? For this example, this is a wind hazard, and this example is you come up with this risk and response matrix, which it combines the likelihood of the event, of the potential impacts of those hazards, determine that risk, and what's the response. So you have on the in this matrix, so you can look and say, okay, based on the forecast, we have, say maybe a medium likelihood of a significant impact. So the risk is medium and the response is, in this case, pre-prepared. If there's a high likelihood, the response to the emergency managers, you want to take action now to prepare and mitigate the risk of the event. So here's just an example from our implementation in Barbados. In this case, the forecast would indicate that there's a minor impact, a likelihood of a minor impact of, in this example, of rainfall in the central part of the island. So the forecasters would identify where's the possible hazard, what's the most appropriate impact level, what's the expected likelihood, and then they create the appropriate risk level. In this case, in a color-coded, easy to understand messaging. And then that messaging is communicated to the emergency managers to then communicate that out to the public. In terms of partnerships and collaboration, we found that a successful partnership is when the Met Services work together with other agencies, especially the emergency management agencies, to develop a cohesive impact-based framework. And they work together in sharing information such as data between agencies in terms of democratics, the risks, GIS mapping, economics, road networks, everything that helps build this successful partnership. Yeah, and then just kind of last, just kind of summarize what I've talked about today is really changing the paradigm shift of a forecast to be going from what the weather will be to what the weather will do. And this provides really an opportunity for Met services to work together for this building this common framework. And the successful outcomes of this type of development is it really improves early warning of high impact weather events, and then and hence it provides improved security and safety to your communities that you're warning for. So with that, I'll stop there. That's just a kind of a short overview of a great I think program and stuff that we developed for Barbados and other regions, and I'll be happy to entertain any questions on impact-based forecasting or the 3D PAWS observation network at this time. So thank you very much for the opportunity to talk again.
Thank you, Paul. Thank you. And yeah, this is a topic which is really gaining a lot of interest, and I mean, most of the Met services are gearing themselves to. So this is something of great interest. Any questions from the participants at this point? So I guess I think most of the presentations are quite clear. Yeah.
Sir, may I say just a small query, please?
Yes, go on, Mohan Kumar Das.
Yeah, thank you, sir. Thank you very much for the opportunity. It is really a very useful talk on the demand of the community people. Actually, community demand is very much focused in this presentation. So just one small query: how community need is assessed? That is important. Whatever the metrics is shown, this is very useful. It will be useful for the community. But how it assess? This is the simple query for the presenter. Thank you. Thank you very much. Best regards.
Yeah, thank you for the.
I like to address this issue of impact-based forecasting, since I'm very much related with aviation, as I'm working in Bangladesh Air Force, and we really practice this impact-based forecasting in Air Force, like what is shown in metrics. But what I faced by practicing this impact-based forecasting is that understanding of forecast or understanding the impact. Here in aviation business, most of the people are educated. I'll say that well educated. But if I consider this area, especially the South Asian region, education is a big problem for understanding the forecast, and also getting the technology, understanding the technology. So have you considered this thing for applying the impact? You have given examples of some area, but have you considered for applying this globally?
Over to you, Paul.
Yes.
Paul, would you like to take those two questions together? I think we are not able to hear you. Paul, I think maybe you're on mute or something.
I think Paul is not listening the.
Paul, are you able to hear us?
Yeah, I can hear you good. Can you hear me now?
Yeah, now it's okay. Now it's okay. Please go on. We have two questions, which are quite, I think, slightly overlapping. Did you hear them well?
I did.
Okay.
I'll address the second one first because I remember that the most in terms of providing impact-based forecasting in a global sense in terms of training for various hazards. And what we've done, or what we do when we go to various regions, is that we work with the stakeholders first to define the needs of the region. What are the hazards? What are the sectors that really need this information? And then we build the training to address those needs. So, for example, aviation, we would provide training on understand the impacts of the weather that would affect aviation operations. So that's what we like to do, and so it's tailored based on the partnerships we work with in the different regions. And the first question, could I get reminded again what the question was, please?
I think it was also linked to the second question. So in some sense, you have already answered it. I mean, the first question was again, you have all this risk categorization, but when you go to the ground level, it's difficult to actually, in the real life situations, to identify and put these boxes probably. So I'm sure you appreciate that. Thank you.
Yes. And again, we work we work closely with the stakeholders of the region. So emergency managers, aviation, for example, transportation, hospitals, and we get their input on where are their risks at, what needs to be addressed. And so working together, they help define the hazards, the impacts, the risks to the region. So that's how a system is built up from the ground upwards, and then adapted for the different regions.
Thank you, Paul.
I think regarding Mohan's questions, I think I can give some compliment. This is Dr. Mannan from Bangladesh Meteorological Department.
Yeah, Dr.
I think rigorous survey system can be adopted for taking the information from the local sites regarding different hazards. In case of Bangladesh, it can be for cyclone, it can be for flood, it can be for heat wave, it can be for cold wave separately. Then things can be formulated because some forecast are there and forecast information is already there, but triggering mechanism, that means for impact analysis, how much temperature would be the optimum for particular purposes or particular cases, and what would be the optimum wind speed for a particular area, which will give that means enormous disastrous situation. That sort of things has to be adopted for first. In that aspect, I think Bangladesh Red Crescent Society with the German Red Crescent Society has already adopted this impact-based forecasting in the case of cyclone and flood. During the last 2 seasons, in the case of cyclone Amphan, as well as during the flood situation in Bangladesh case, they have been adopted and they have been activated this forecast-based financing based on the information gathering from Bangladesh Meteorological Department with the consent of us, as well as with the information provided by the flood forecasting and warning center. So after the happening the event, they again reanalyzed the system, and they were having that opinion that more that means analysis should be conducted before activating this sort of forecast-based financing. So I think Paul can agree with that one.
Thank you, Dr. Mannan, for clarifying the situations in Bangladesh. So I think, Paul, would you like to add?
The thing is not that easy to implement, because the impact of the same phenomena can vary place to place and time to time. So it is not so easy to implement that type of forecast by the originating centers. There should be one type of translator or stakeholders who can convey and translate the weather forecast to the impact based forecast necessary for the user level. So, and that would be a very continuously changing process. Say, for a forecast of dense fog, maybe if there is any highway, the transport would be disrupted, and if there is a tomato field, then they should apply uh, some kind of uh, some kind of uh, uh, pesticide or other things to protect their crop. So impact is different for a very maybe very adjacent areas. So it is not so easy to implement that type of things, and not for the originating centers.
Yeah, thank you. Thank you. I think, Paul, would you like to respond to that very briefly? Because already I think we are running out of time. Thank you.
Yes, I was just going to mention that I agree with that that message, that it requires coordination, say with the Met Service and the other agencies to really convey the messaging that for the impact for the different sectors, different regions, and that messaging is very important. And it takes what we found quite a bit of time and work to really come up with the proper messaging. In the goal of the forecasters provide the best information about what the forecast is to convey what the impact is. So as you say, I like to use the example of so maybe at the beginning of the forecast, there has been little rain, there's a little likelihood of flooding, but as more and more rains come due to storms, that likelihood goes up that flooding is going to occur. And that, so you're constantly monitoring soil conditions, river flows, like this, and then you're updating that messaging that can be conveyed to the public to take warning based on those messages. So anyway, it is a somewhat hard thing to implement, but very useful and helpful to society once it's in place. So.
Thank you, Paul. I think that's the challenge of impact-based forecasting. Of course, that's very it needs a lot of coordination and working together with very diverse kind of communities, sectors, and government departments, and so on. So at this point, maybe I will request my co-chair, Professor Zilur Rahman, to say some words and wrap up this very interesting session, which had 5 presentations. So all of them were very high quality and very nice and relevant to our work in the region. Over to you, Professor Rahman.
Thank you, Dr. Govinda Rajalu Srinivasan. Thank you very much. I would like to thank you to chair this session and moderating this session very nicely and very effectively. So thank you very much. So in this session, we had 5 technical papers that were presented here. And I'd like to thank all of the presenters for their nice, interesting, informative, and valuable presentation. All are relevant to the title of this session, the application of technology in meteorology. So this presentation covered detection of lightning. The lightning is very important incident in the subcontinent because the death due to lightning is increasing day by day in this region. So So we need to detect it and we need to prevent it. Hundreds of people are dying due to this lightning in Bangladesh too. So earlier it was not declared as a disaster. Now government has declared lightning as disaster. So it is very time effective. It is very timely presentation, and we need to use new technologies for detecting lightning. So it is very relevant to this session. And next presentation was use of 3D printing for weather establishment of weather networks. It is also very timely presentation. So we need to use these types of technology in this era of fourth industrial revolution. So we are in the fourth industrial revolution. We need to use modern technology for our development. So we have to use this one. So it was very nice presentation. And the third one was next generation seasonal prediction system for Bangladesh. So this also very timely presentation, and using technologies we can predict the system, seasonal prediction system. We can improve this for Bangladesh as well as in the subcontinent. It was very relevant presentation for this session. And connecting resource for developing advanced weather forecasting expertise, it's also very relevant, because for you to use technology need proper training. Now technology proper training to establish any establishment or any forecasting station or weathering monitoring station any for this one. So it was also very nice. And impact based forecast, it is also we need this now. We need to adopt these types of technology, impact based forecast and warning system, because we are now going to impact because we need to use this one. This one's fifth one, okay, fourth one. And impact based, suppose risk based, risk informed, and impact based, these types of procedure we need to use. Because if I know the impact, if I know the impact, we can disseminate this impact to the stakeholder, and they can prepare for this, what will be the consequence of this disaster. So it is also very important presentation. So I think all of this presentation was very nice and informative, and using of science and modern technology, we should improve this to reduce our disaster and to improve our meteorological forecasting and warning system. So it was very nice session, application of technologies in meteorology, and that's so I would like to I'd like to thanks the organizer of the conference for organizing such an important conference to enrich our knowledge and to show the. So I would like to thanks again the conference convener, Professor Dr. Tohida Rashid, for her this effort, and he is also chair of the meteorology department of Dhaka University. So it was a wonderful presentation, wonderful conference. So thank you very much, Professor Dr. Tohida. And the member, he worked very hard. I saw he mailed us several times. He sent a SMS several times and frequently. And I want to thank Shurab for his effort. So thank you very much, Dr. Govinda Razalu Sri B Srinivas.
okay.
Srinivas. It is okay?
Yeah,
Srinivasan?
it's okay. You can.
Srinivasan. So,
Srinivas.
okay. Thank you very much. Thank you very much.
Thank you. Thank you,
For
Professor
your
Zilur
presentation
Rahman.
and for your time. Okay. Thank you all the presentation for your valuable time, for your nice presentation. Thank you very much.
Yeah, I think with that we can wrap up the session. Absolutely great that we still have 32 participants, and it was excellent, like Professor Rahman very clearly summarized. So this is particularly, the session is interesting for me because we are in the cusp of just launching a project along with the World Bank on South Asia Hydromet Forum, which is aimed at capacity building efforts in the region. So I think I will be in touch with some of our COMET colleagues who are here. So it will give us an opportunity to take those things forward when we start implementing this program. And as I said earlier, the lightning system, we are already using it. And I am sure that with this data, which will be made available, a lot of students in Dhaka University, as well as many other universities in the region, would be able to do much better analysis with lightning and convective activity in the tropical areas, which is very important. And Dr. Keta's work will really help the operational seasonal prediction process. So thanks to all the presenters. I think it's been a very interesting session. Over to you, organizers. Thank you. I think you are muted.
Please unmute it. Okay.
Thank you, sir. Thank you, Honorable Chair and Co-Chair, for conducting the session, and all the presenters for their wonderful presentation. Now I would like to thank all the attendants for their presence. List of the session of the conference will be continued tomorrow. Tomorrow's session will be started from 9:45 in Bangladesh Standard Time. So all are invited to join the session tomorrow. Till then, goodbye and thank you all. Thank you, sir.
Thank you very much.
Thank you, Professor Rahman.
Thank you, Doctor.
Very nice to meet you virtually.
Yeah, good night,
Okay,
everyone.
nice to meet you.
Yeah.
Thank you for joining us.
Yeah, Professor Rashid, thank you. It's been excellent. Your team has done a really great job. So we really congratulate.
But without your cooperation, it would not be possible. Thank you all. Thank you, thank you so much.
It was a great session.
Good night.
Thanks.
Bye.
Thank you,
See
Paul. Thank
sometime
you.
later. Bye. Yeah.
Bye-bye.
Thank you. Bye-bye.
Bye-bye. Liz, how are you? Bye.
Good. How are you? It's good to see you.
Yeah, good to see you again.
It's an excellent conference. Thank you so much for allowing us to participate.
Yeah, please enjoy the conference, because yesterday we have another 5 sessions, I think. So
yes.
you
Yes,
must
yeah.
be
So I
here.
look forward
Yeah,
to it. I'll
please.
be on again tonight for us. Yeah.
Yeah. I mean, morning too. I mean, like it's a whole day
Exactly.
conference.
Yeah. Oh yeah. I thank you for accommodating us.
Thank you so much. Okay.
Bye.
Good
Bye-bye.
night, everyone, and good morning. Bye.